I'm going to presenting my work on assignment one, question two, um, for the AI programming course. So this assignment focuses on predict vehicle fuel efficiency using deep neural network. We'll be working with a UCI Auto MPG dataset to build a regression model that predict miles per gallon or MPG. So the main text include the data pre-processing, handling missing values, training a DN regression model, and making prediction for 10 test vehicles. So let me walk you through my implementation. So this notebook is organized into several main sections about the setup, automatic packet installation to ensure all dependencies are available, data loading, reading the auto MPG dataset from UCI repository. So the part A, dropping the name and origin attribute as required. Part B, um, filling 6 missing horsepower value using the average horsepower for the respective number of cylinders. The part 3, convert the 2-digit year value to 4-digit format by adding 90. Part D is about the splitting the data into 50-50 training and the validation sets. And part E, building and training a deep neural network for MPG protection. And as we can scroll down, part F, using the train model to predict MPG for 10 test vehicles. And finally is the detail about the code attribution. So let's start with the data processing. As you can see, we have a we have 398 rows and 9 columns. And there are 6 missing values in the horsepower column. So part A, I dropped the car name and the origin attribute using the drop method. Is leave us with the 7 columns. And for the part B, this is the important part I designed myself and use a group by to calculate the average horsepower for each cylinder counts. For example, 3-cylinder cars average 90.25 horsepower. A 4-cylinder car's average is 78.28, and so on. So then I use the math function to fill missing values based on the set cylinder count. This strategy makes sense because horsepower is strongly correlated with the number of cylinders. The part 3, the original data set has 2-digit year like 70, 71, 72. And at the 1900 or to convert them to 4-digit years. So now the year range is probably formed from 1970 to 1982. So all these pre-processing design were made by me based on the understanding the data and about the assignment requirement. So about the part D, um, as per the feature X and the target Y, which is MPG, then I use a train test spelling with the test set equals 0.5 for a 50-50 spell at the required. Like you can see from the output is a training set says about the 199 samples, validation sets in size 99 samples. So we have that samples in the training set and with the 6 features each. Then I use the standard color to normalize the features. Is crucial for neural network became feature lightweight, which range from 13 to 5140. and the acceleration, which range from 8 to 24, have very different scales. And standardization bring all features to a similar scale, so which helps the model train more efficiency. Now part E, building the deep neural network. So I designed the three hidden layer architecture with the 64, uh 32, and 16 narrow respectively. So let me explain the key design decision I made. First is that each layer follows the patterns design layer. Um, and second, I use an L2 regularization with strength of 0.001 on each design layer to print an off feeding. So this value was chosen based on my understanding about of typical L2 value from the small for the small data set. And third one, batch normalization is stabilizing training by normalizing by input to each layer. And fourth, I choose a leak value with alpha equals 0.1 instead of standard value of to avoid the dying value problem. And I use the normal initialization, which is a recommended for value like activation. So this output layer has only one arrow because this in is a regulation text. We are protecting a continuum value MPG, not the class label. For regulation, I use a mean square A to add loss function and track both MAE and MSE on the matrix. And let me show the training process. So I implemented two callbacks. Early stop with a patient of a 40 epochs, which stops training if validation loss doesn't improve, and reduce the learn plot, which reduce the learning rate by half when the validation load impact. You know, I trained for up to 500 epochs with a batch size of 32. You can see the show the picture of the models and about the mean absolute error. The right graph shows the both curve coverage around the 1.8 to 1.9 mpg, which means our model is a prediction and typically off by lanes than 2 miles per gallon. And the left graph shows the loss, the blue training loss and orange validation loss decrease together and stay close to each other, which is a good sign. It means to the model is not the overfeeding. And for the performance, uh, the validation MAE, training MAE is a 1.87 mpg. The validation on MAE is 1.83 mpg. Is actually slightly better than training MAE, which indicated good generalization without the overfeeding. So this performance was achieved through the regularization technique I implement. And for the part F, is the most interesting part. Is predict the MPG for 10 test vehicles. So let me analyze the predictions. So vehicle 1 to 4, marked with the asterisks. This have a actual main spec function. Vehicle 2, for example, has still standards 6478 displacement and 730 horsepower. These are far outside the training data range. The model predict 38.30 mpg, but in reality, such a powerful vehicle would likely get much lower mpg. This shows the limitation of the neural network. They struggle with the extrapolation beyond the training distribution. And I see the vehicle 5 is a more than small car with a 4 cylinders, 181 horsepower, and well, is that in the year 2025, the prediction is 47.40 mpg. So the vehicle 6 is from 1969 within the training data range. The prediction of uh 28.03 mpg seems reasonable for the vintage car. So the vehicle 7 and 8, there's the 3-cylinder vehicles with very low weight get the prediction of 48.2 and the 53.4 mpg. The high volume makes sense because low weight typically is mean better for efficiency. The vehicle 9 and 10 are from 96.4 and 90.08 is far outside the training range. Vehicle 10's prediction of a 22.89 mpg is unreliable because the model has no information about early 20th century technology. So it's about the uh, reasonable section. I wrote the detailed analysis explaining why certain predictions are reliable and others are not. The key insight is that machine learning models are interpolars, not the extrapolators. The work based on data similar to what they were seen during the training. For vehicle with the 9070 to 9082 range with a reasonable specific factor, the prediction should be trustworthy. For extreme case. We should interpret the result with a caution. To summarize, in this assignment, I have successfully to pre-process the auto MPG dataset, handling missing value intelligence, and build and train deep neural network for regression, achieve validation MAE of 1.83 mpg, and made the prediction for 10 test vehicles and analyze their reliability. Understood the limitation of neural network when extrapolating beyond the training data, and this document all code source and on stage report like which part I use the AS instance. So thank you for the watching for this presentation. And this is about my question to automate MPG prediction.